Okay, folks, I'm going to go ahead and get started. As mentioned last week, I will start doing some lecturing at the beginning. What I'm going to go over today is at least part of what you need to know in order to complete the lab. I hope to finish off the majority of what you need to know in order to complete the lab on Thursday of this week, so that you'll have all the information you need to actually do the post-lab results. You can do the lab. I mean, the lab itself is easy and straightforward. It's just you need the information in order to complete the post-lab and data sheet. So previously, I introduced chemical equations. When we deal with a chemical equation, on the left-hand side, we find the reactants. On the right-hand side, we find the products. The reactants and the products are separated by a yield sign, which is an arrow. Now, when we were talking about the chemical equation, I said that not only should you include the identity of the reactants and the identity of the products, but you should also include their state of matter. Now, states of matter, to some degree, is just a result of experience. But as I will discuss in this first portion of the lecture today, it is also the result of knowing some information. There is some information that can guide you, in other words. Now, before I get into that information that guides you into determining the state of matter, I want to discuss the concept of an electrolyte, because this concept of an electrolyte is going to play directly into much of what we'll be discussing for the remainder of this chapter. So this chapter began with a discussion of solutions. A solution consists of a solute and a solvent. And when the solute and solvent combine, you form a solution. Now, when we talked about a solution, we talked about it in terms of molarity. And that is where we started our conversation. Now, if we're going to discuss a solution, we need to get a better understanding of what goes on with the solution process. So you have your solvent. The first thing that must occur is you must add energy in the form of an enthalpy to that solvent in order to break down the forces that keep the solvent molecules in close proximity to one another. With the solute, you must do the same thing. You must take and introduce energy, typically in the form of enthalpy, in order to break down the interactions between the individual solute molecules, allowing the solute molecules to spread out. Now, once the solvent molecules have spread out and the solute molecules have spread out, then energy is given off when a solution is formed. Now, whether a solution will form or not is really dependent upon these energies. If the enthalpy associated with solution formation is equal to or greater than the enthalpies associated with separating the solute and separating the solvent, then a solution will form. But if the enthalpy associated with solution formation is less than the enthalpy associated with separating the solute and the enthalpy associated with separating the solvent, then a solution will only form if outside influences are added. Now, once these solutions form, solutions can be described as an electrolyte or a non-electrolyte. The term electrolyte basically indicates whether a solution will conduct electricity. An electrolyte is a solution that conducts electricity, whereas a non-electrolyte is going to be the result of a solution that does not conduct electricity. So what is it about the solution that allows some solutions to conduct electricity while others do not conduct electricity? The answer comes down into what happens when that solute dissociates. If, for example, like table salt, when the solute dissociates, if you have individual cations and individual anions that are free floating in solution, then you can get the conductivity of electricity. But if you do not have free floating ions in solution, then it will not conduct electricity. So an electrolyte is a substance that when it dissolves forms ions in solution. Whereas a non-electrolyte is a substance that when dissolved does not form ions in solution. Now we can classify an electrolyte based off of the degree to which it conducts electricity. So an electrolyte, again, is a solution that conducts electricity. In order for it to conduct electricity, you must have free-floating charged particles that are allowed to move around in the solution. Some substances can be classified as strong electrolytes because when they are added to water, they dissociate entirely into ions. These substances are soluble ionic compounds and strong acids. If you add a soluble ionic compound to water, it's going to dissociate entirely into its ions, and therefore it will conduct electricity because you'll have free-floating ions. If you add a strong acid to water, it's going to dissociate entirely into its ions, and therefore you will have free-floating ions and it'll conduct electricity. Now, some compounds, they are weak electrolytes, meaning they conduct electricity, but they don't conduct electricity well. A weak electrolyte is going to be a substance that only partially dissociates in water to form ions. Weak electrolytes include insoluble ionic compounds. Now, the term insoluble typically means that it does not dissolve. And so it's a little bit of a misnomer because all ionic compounds dissolve to some degree. It's just there are many of them out there that dissolve only to a minuscule degree rather than to a significant degree. So weak electrolytes would include your insoluble ionic compounds. It also includes your weak acids and weak bases. And then your non-electrolytes are going to be molecular compounds. If you'll recall on the last exam, one of the questions I asked you is whether a substance was an ionic compound or a molecular compound. One of the reasons you needed to know that is for this purpose. Ionic compounds are going to be compounds that contain metals. Molecular compounds are going to be compounds made up of nonmetals and metalloids only. And your molecular compounds will tend to be non-electrolytes, except for your acids and weak bases. Now, let's talk about states of matter. I said when I started this conversation that part of this is being able to understand the state of matter. And I'll reemphasize these along the way. Your soluble ionic compounds will have the state of matter in water of aqueous, meaning they dissociate entirely. As will your strong acids. They will have the state of matter of aqueous in water. Your insoluble ionic compounds will typically be listed as a solid in solution. However, your weak acids and weak bases, those will also be listed as aqueous in the reaction. Now, your molecular compounds, it really is dependent upon what the molecular compound is. With acid-base reactions, one of the substances is water. Well, if you have pure water, we typically list it as a liquid, unless we know that it is in ice form or in steam form. But we typically list it in these reactions as a liquid. But for example, sugar, when it's dissolved in water, would be aqueous, but it's not going to be a conductor of electricity. So it really is dependent with those molecular compounds, what the compound is, how soluble it is in water, as to what state of matter we provide in the reaction. So again, going back to the ionic compounds, your soluble ionic compounds will be strong electrolytes, meaning that they dissociate entirely into ions in water. We will give the state of matter as aqueous for these materials in the balanced chemical equation. Your insoluble ionic compounds will be compounds that do not dissolve in water, even though, as I just said, that is really an oversimplification, something that will be discussed in greater detail in college chemistry too. But for our purposes, if it's an insoluble ionic compound, we will list it as a solid in water. So how do we know whether it's soluble or insoluble? We use the solubility rules. Now, I will give you the solubility rules on exam 4, so you don't have to memorize them. However, you need to know how to interpret them. And the solubility rules really are listed in order of importance as far as how you approach things. Rule number 1 and rule number 2 in particular are extremely important. The reason rule number 1 and rule number 2 are particularly important is because that there are no exceptions to these rules that we are going to discuss in our class. Rule number 1 is that if it consists of a group 1 metal, or if it contains ammonium as the cation, it is soluble, meaning it is aqueous, and there are going to be no exceptions to that rule. The second rule is if the anion is a nitrate or an acetate, or in many cases a chlorate, the substance is going to be soluble, and there will be no exceptions to that rule. Now, what you will notice is that the first rule is the only one that focuses on cations. The rest of these rules focus on anions. Rule number 3 says that your chlorides, bromides, and iodides will be soluble, but there are, meaning that they will be aqueous. So the majority of chlorides, bromides, and iodides are aqueous. There are 3 exceptions to that. One is if it's combined with the silver ion, one if it's combined with the mercury 1 ion, and the last is if it's combined with the lead 2 ion. If it's combined with those 3, any of those 3 ions, then the halogen will be insoluble, meaning it will be a solid. Sulfates are very similar to the chloride, bromide, and iodide. Most sulfates are soluble, meaning that they will completely dissolve in solution. But there are some exceptions. You will notice silver and lead come back. I believe mercury 1 also comes back. But now we've added 3 additional ones. We've added strontium, barium, and calcium to that list as well. Now, the top portion of this talks about the ions that are soluble, meaning aqueous, with a few exceptions, meaning these would be solids. But the bottom portion of this table focuses on the ions that tend to be insoluble, meaning they will be solids in an aqueous reaction. The first one I want to point out is the hydroxide and the sulfides. Hydroxides and sulfides tend to be insoluble, meaning they tend to form solids. Now, you will notice rule 1 is an exception. Rule 1 is, again, if you'll do them in this order, specifically rule 1 and rule 2 first, you will take care of a lot of compounds. But hydroxide and sulfides tend to be insoluble. Now with sulfides, the exceptions are when they're combined with calcium, strontium, and barium. When you have calcium sulfide, strontium sulfide, or barium sulfide, those tend to be aqueous. But all the rest of the sulfides are solids. With hydroxides, again, the other exceptions besides group 1 is your calcium, strontium, and barium. And calcium, strontium, and barium tend to be slightly soluble. What's interesting is with respect to the hydroxide here, except for ammonium, all of the rest of the hydroxides that are soluble also are your strong bases. So your lithium, sodium, potassium, rubidium, those are all strong bases, as are your calcium, strontium, and barium. And then we have carbonate and phosphate. Carbonates and phosphates almost entirely are insoluble compounds unless they're combined with rule 1. That's why rule 1 is so important. Rule 1 lists several of the exceptions right off the bat. Any questions about the solubility rules? You will be using the solubility rules to work with some of the reactions that you'll be performing today. Now, how do you know that you have a solid forming as part of the reaction? You're going to look for the reaction to become cloudy. Now, in the definition of electrolytes that I gave you. Another electrolyte that I gave you was that of an acid. Acids can be either strong electrolytes or weak electrolytes. Acids, no matter whether it is a strong acid or a weak acid, are going to have the state of matter of aqueous. An acid is a substance that, when added to water, dissociates to form a H plus ion, sometimes referred to as a proton. Now, a proton cannot exist on its own. So you can't have free H plus floating around. So what happens is the H plus combines with the water molecule to make the hydronium polyatomic ion. So again, an acid is going to be a substance that makes an H plus when added to water. Now we use this H plus and this hydronium interchangeably, understanding that, again, you can't have a free floating proton, and therefore the proton has combined with water to make hydronium. Here I have given an example of hydrochloric acid. Hydrochloric acid, the hydrogen from the hydrochloric acid reacts with the water to form the hydronium ion, and what's left over is the chloride ion. Down here, I've given you acetic acid. The acetic acid reacts with water. The acidic hydrogen of the acetic acid combines with the water to form hydronium, and then what's left over is the acetate anion. This is the process anytime you have an acid in water. Again, all acids, whether they're strong or weak acids, will have the state of matter of aqueous in the balanced chemical equation. So how do you know who the acids are? Who's a strong acid? Who's a weak acid? There are 7 strong acids that you must memorize. They are hydrochloric, hydrobromic, hydroiodic acid. In other words, they are the 3 middle halides on the periodic table. The others are acids of polyatomic ions. They are nitric acid, perchloric acid, chloric acid, and then the only diprotic acid, sulfuric acid. These are your strong acids. You must know these acids. You must have them memorized. If it's not one of those 7 strong acids, then it is a weak acid. So your weak acids can include things like oxalic acid, which we worked with last week in the laboratory, sulfurous acid, phosphoric acid, nitrous acid, benzoic acid, acetic acid, and formic acid. Now, with respect to these acids, you will notice something about their formulas. In the case of all of the strong acids, the acidic hydrogen is listed first in the formula. With respect to the weak acids, the acidic hydrogen is listed first in the formula, or it has this COOH group called a carboxylic acid. In the case of a carboxylic acid, the hydrogen attached to the 2 oxygens is going to be the acidic hydrogen, which I just specify over here. So again, your strong acids, you have to memorize them. Your weak acids will be all other compounds that start with hydrogen or have a carboxylic acid functional group. Those are the ways that we indicate that you're working with an acid. Either the formula starts with the acidic hydrogen, or we indicate the carboxylic acid functional group. Again, strong acids are strong electrolytes. They dissociate entirely in solution. Weak acids are weak electrolytes. They only partially dissociate in solution. All of them have the state of matter of aqueous. Now your strong bases. Again, I've already mentioned this, but if you looked at your rules for the soluble hydroxides, you would see that your strong bases fit the definition of a soluble hydroxide. So really, you just need to know your solubility rules to know who is a strong base. Now, what about the weak bases? The most common form of a weak base, you will notice all of the ones that I gave you have an NH group. That group is called an amine. And it is indicative of a weak base. Again, whether it's a strong base or a weak base, they're going to have the state of matter of aqueous. So strong bases are soluble ionic compounds, or the slightly soluble ionic hydroxides. Your weak bases are going to be your amines. They can have, you can have 0 to 4 hydrogens on that nitrogen, and it counts as a weak base. Questions? Okay, let's see what you remember. So the first thing is, will these solutions conduct an electrical current? In order for them to conduct an electrical current, what must exist? Free floating ions. What's going to give you free floating ions? Strong electrolytes and weak electrolytes. The stronger the better, meaning the more soluble the ionic compound, the better, because that's going to give you the most ionic charge in solution. So, rubidium bromide. We would expect rubidium bromide to dissociate to form rubidium ion and bromide ion in solution. The reason we would expect rubidium bromide to break apart into rubidium ion and bromide ion is because of Rule 3 of the solubility rules. So this is going to be an electrolyte. Sodium hydroxide. Because of Rule 1, we know this is going to dissociate into sodium ion and hydroxide ion. So it is going to be a good electrolyte. The sucrose. Because this is a molecular compound, and it's not an acid or base, that means that this is a non-electrolyte. It is not going to conduct electricity. Magnesium sulfate is going to dissociate to form magnesium ion and sulfate ion because of rule 4 of the solubility rules. So it is going to be a good electrolyte. It is going to conduct electricity well. Potassium sulfate. Potassium sulfate is going to dissociate to form 2 potassium ions and a sulfate ion. This is going to be rule 1 of the solubility rules, and therefore we would expect it to be a strong electrolyte. Glucose is a molecular compound, and it's not an acid or base. And so we would expect this to be a non-electrolyte. Potassium carbonate is going to dissociate into 2 potassium ions and a carbonate ion. And because of rule 1, it is going to be a strong electrolyte. The last one is a molecular compound. We know this is molecular because it consists of nonmetals and metalloids only, and it is not an acid or a base. And so we would expect this to be a non-electrolyte. Now, one thing I do want to point out, when I dissociated these compounds into their ions, you will notice that any subscript that is present in order to make the compound charge neutral became a coefficient when the ions were dissociated. Again, any subscript that was there to make the compound charge neutral became a coefficient in the dissociated reaction. Let's look at a couple more. Soluble or insoluble? List the ions present in solution if it's soluble. Silver nitrate. Silver nitrate is going to dissociate into silver ion and nitrate ion because of rule 2. So it is a soluble ionic compound. Lead acetate is going to dissociate into lead ion and 2 acetate ions because of rule 2. So it is also a soluble ionic compound. Potassium nitrate dissociates to form potassium ion and nitrate ion because of rule 1. And so it's a soluble ionic. Ammonium sulfide dissociates to form 2 ammonium ions plus sulfide ion because of rule 1. And so it's a soluble ionic compound. All of these would be strong electrolytes, meaning they would conduct electricity well. All of these, as we will talk about later when we go in, look into the solution, become the break down into their ions. If we actually were to take a microscope and we were able to actually look at what's going on in solution, we would see these in the form of ions. Now, silver iodide is a solid because it's an exception to rule 3. And therefore it is an insoluble ionic compound. Copper 2 phosphate would be a solid because of the phosphate rule. This is not an exception, and therefore it would be an insoluble ionic compound. Cobalt carbonate would be a solid because it fits the carbonate rule, and it is not an exception. Therefore, it would be an insoluble ionic compound. But potassium phosphate would be a soluble ionic compound that would dissociate into 3 potassium ions and a phosphate ion because of rule 1. And so it is a soluble ionic compound. Questions? You've got to understand this piece to go to the next piece. So let's look at the next piece. Let's talk about precipitation reactions. A precipitation reaction is a reaction in which a solid forms upon mixing 2 solutions. This is the definition based off of your textbook. The solid that is formed is called a precipitate. Again, I've underlined some key pieces. A reaction in which a solid forms upon mixing 2 solutions. We're specifically talking about ionic compounds here. So we're talking about an insoluble ionic compound forming from 2 soluble ionic compounds. An example would be one that you'll be doing today. If I take potassium iodide and I were to hone in on the potassium iodide, I would find that the potassium iodide is a soluble ionic compound due to rule number 1, meaning that there are free-floating potassium ions and iodide ions in solution. If I combine that with lead 2 nitrate, if I hone in on the lead 2 nitrate because of rule number 2, I would see that I would be dealing with a soluble ionic compound where I have free-floating lead ions and free-floating nitrate ions in solution. Now, when the potassium iodide combines with lead nitrate, a precipitate forms. This precipitate is the result of the lead combining with the iodide to form an insoluble solid that precipitates out. The remaining potassium and nitrate are spectators in this process, and they just continue to exist in solution. But the lead reacts with the iodide to form a solid. That is, so in other words, again, we had a soluble ionic compound, which was a strong electrolyte in the potassium iodide. We had a soluble ionic compound, which was the lead 2 nitrate. Those two combined to form an insoluble ionic compound, meaning a solid precipitate, which was the lead 2 iodide. And in this case, we had a soluble ionic compound, which was the potassium nitrate, which was also a strong electrolyte. Now, technically, a precipitate reaction just means that at least one precipitate forms. You could have more than one. Now, if you have more than one precipitate, that is actually typically not a good reaction because we want to separate precipitates. But you could have more than one. All that is required is that you start with 2 solutions and you form a precipitate. Now, potassium iodide with sodium chloride would be an example of a reaction that is not a precipitation reaction. You have potassium and iodide, just like previously, which if you hone in are potassium ions and iodide ions. You react that with sodium chloride, sodium ions, and chloride ions. But if you look at the possible products that form, neither one is a solid. In fact, what you have when you combine these two is just a bunch of ions. So we say no reaction has occurred in that case. So, what is the process for developing the molecular equation, the balanced chemical equation? Well, the first thing we're going to do is we're going to develop the formula of our 2 reactants. We are then going to allow those 2 reactants to combine to form 2 new products. And we will develop the formula of those products using what is referred to as a double displacement reaction, where the cations swap the anion partners. And I'm going to illustrate this here in a minute. So we're going to allow the reactants to combine to form 2 new products. And we're going to obtain these products through a double displacement reaction where we swap the cation partners or the anion partner. Once we have created the formulas for the reactants and the products, we are then going to apply the solubility rules to the reaction to determine whether any of the products formed were a solid. If neither of the products formed were a solid, then we will say no reaction. But if any of the possible products are insoluble, we will write their formula as the products of the reaction using a solid, or an S to indicate a solid, and we'll write any soluble products as aqueous to indicate that they are soluble. Then we'll balance the chemical reaction. Now, let's look at this in action. Well, I guess I don't need to walk over there. So potassium carbonate. We know this contains potassium ion and carbonate ion. We take the magnitude of the charges and we cross and drop them on the opposing ion, and therefore on the potassium we will drop a 2, and we need only 1 carbonate. That is one of our reactants. The second reactant is nickel 2 chloride. So our nickel has a 2+ charge and our chloride is Cl-. We take the magnitude and we cross and drop it on the opposing ion and we get NiCl2. Those are our 2 reactants. So we've taken the names and we have obtained the formulas of the reactants using our names to formulas, which you're tested over tomorrow. Now, we're going to assume this is a double displacement reaction because we're dealing with 2 ionic compounds. And if it's a double displacement reaction, it means that the cations are going to swap the anions they are associated with. So our potassium is now going to be connected with the chloride. And the nickel 2 is going to be connected with the carbonate. And we're going to create our formulas based off of these ions. And so it would be KCl and NiCO3. Both of them in a 1-to-1 ratio because that is what is necessary for the charges. So now what we've done is we've created the products. Note, folks, one thing I want you to note is I did not simply pick up the formula from here and drop it over here. You can't do that. You have to go back to its ions. You have to go back to the ions and figure out what the formula would be based off of the ions. Now, we're going to use the solubility rules to determine whether they are soluble or insoluble. Potassium carbonate is going to be aqueous because of rule number 1. Potassium chloride is going to be aqueous because of rule number 1. Rule number 1 saying any group 1 metal or ammonium is going to be aqueous. Nickel 2 chloride is going to be aqueous because of rule number 3, which states that chlorides, bromides, and iodides are soluble except for lead 2+, silver, and mercury 2+. Since this is not one of the exceptions, it means it follows the solubility rules and therefore it is soluble. Nickel 2 carbonate, however, is a solid. We know nickel 2 carbonate is a solid because the carbonate rule says that all ionic compounds are insoluble or solid, in other words, except for group 1 and ammonium. Since this isn't one of the exceptions, it means it follows the solubility rules and therefore it is a solid. The last thing we need to do is balance this reaction. So we need to add 2 potassiums to the or 2 as the coefficient to potassium chloride in order to balance the reaction. You've got to be prepared today. Well, by the time this lab's due, to do this. Now, this lab isn't due until next week because we're not going to have gone over everything until next week. But you got to be prepared to develop the molecular equation using the process that I just did. Okay. Now, for the last bit. Representing aqueous solutions. What I just did was develop the molecular equation for a precipitation reaction. But there are other ways that we can represent a reaction. The molecular equation probably is the least informative of what is actually going on in solution. Probably the most informative is the complete ionic equation and then the net ionic equation. So what are they? Molecular equation is an equation that shows the complete neutral formulas for each compound in the reaction as if they existed as a molecule. But we've already talked about the fact that if we're dealing with soluble ionic compounds, they don't exist as molecules. They exist as ions in solution. So that brings up the complete ionic equation. The complete ionic equation is an equation that shows all strong electrolytes as ions in solution. And yes, I've emphasized strong electrolytes because we're only going to dissociate the strong electrolytes, meaning we're only going to dissociate your soluble ionic compounds and your strong acids. You do not dissociate anything else but those two. Finally, the net ionic equation. The net ionic equation simplifies the reaction to illustrate only the substances that undergo a change by removing any spectator ions, where a spectator ion is an ion that looks identical on the reactant side as it does on the product side. So let's look at an example. A minute ago, I gave you the reaction of lead to nitrate reacting with potassium iodide to form lead to iodide and potassium nitrate. We said because of rule number 2, lead to nitrate was a soluble ionic compound, which means it is a strong electrolyte. We are therefore going to dissociate lead to nitrate into its ions as we go to the complete ionic equation. Now you will note that the subscripts, just like I mentioned previously, the subscripts that are there in order to make this charge neutral become coefficients in the complete ionic equation. Potassium iodide. Due to Rule 1, is a soluble ionic compound, meaning it's a strong electrolyte. So we are going to dissociate it into its ions. Note that the two coefficient preceding the potassium iodide was distributed to the potassium and the iodide because a coefficient of 2 means that you have 2 of those formula units. So you have 2 potassiums and 2 iodides. Because of rule number 3, lead 2 iodide is an insoluble ionic compound, meaning it is a weak electrolyte. We don't dissociate weak electrolytes, and so it was pulled down as is into the complete ionic equation. Potassium nitrate, because of rule 1, was a soluble ionic compound, meaning it's a strong electrolyte, so we dissociate potassium nitrate into its ions of potassium ion and nitrate ion. Notice again that the coefficient of 2 was distributed among both the ions because of the fact that that 2 coefficient means that there's 2 of those formulas. So that means that there's 2 potassiums and 2 nitrates. Now, to go from the complete ionic to the net ionic, we remove spectators. A spectator is going to be an ion that appears the exact same on the reactant side as it does on the product side. On the reactant side, we have lead 2 plus aqueous. Do we have lead 2 plus aqueous on the product side? No. So that's why the lead 2 plus was brought down. On the reactant side, we have 2 nitrate aqueous. Do we have 2 nitrate aqueous on the product side? Yes. Therefore, nitrate is a spectator ion. On the reactant side, we have 2 potassium ion aqueous. Do we have 2 potassium ion aqueous on the product side? Yes. Therefore, potassium is an example of a spectator ion. On the reactant side, we have 2 iodide aqueous. On the product side, do we have 2 iodide aqueous? No. So that's why it was brought down. And then the lead iodide was brought down. Notice that what was in the net ionic is only the substances that underwent the change. So let's look at one more example. Strontium chloride and lithium phosphate. We're going to put everything together except for the identity of acids and bases today. Strontium chloride. Strontium is Sr2+. We know it's a 2+ because it's in group number 2. Chloride is Cl-. We know that it is Cl- because it's in group 17. The formula, therefore, for strontium chloride is SrCl2. Lithium phosphate. Lithium is Li+. We know it's Li+1 because lithium is in group 1. Phosphate with the ending ATE tells me that it's a polyatomic, and it is the polyatomic PO43-. The formula for lithium phosphate, therefore, has to be Li3PO4. Now, I love actually working again with the words and translating the words because it makes the next step easier. And that is to develop the formula of the products. Because we're starting with 2 ionic compounds, it means that this is a double displacement reaction, meaning that the cations will be swapping the anions they're attached to. So strontium will now be attached to phosphate. Taking the magnitude and crossing and dropping, it'll be SR3PO4 2. And then lithium chloride will be LiCl. We now have the formula of our reactants and our products. Now we need to determine the states of matter. We're going to determine the states of matter using the solubility rules. Rule number 1 says anything that has a group 1 or ammonium is soluble. Therefore, our lithium phosphate is going to be soluble. Our lithium chloride will also be soluble. Because it has group 1. The next rule deals with nitrates and acetates. So we move on to the rule number 3. Rule number 3 says halogens are soluble unless it is silver, lead 2, or mercury 2,2+. Since this is none of those, that means that it follows the solubility rules, and therefore this is aqueous. Now we have strontium phosphate. Moving down to the phosphate carbonate rule. Phosphates are insoluble, meaning a solid, unless they're with group 1 or ammonium. Since this follows the solubility rules, that means that this is a solid. The next thing we need to do is we need to balance this equation. To balance this equation, we're going to need 3 strontium chlorides, 2 lithium phosphates, and 6 lithium chlorides. And that is your molecular equation. Now let's get to the complete. Before I even do that, I go through and take a couple of seconds to go, is it soluble ionic and a strong electrolyte, or is it insoluble ionic and a weak electrolyte? Because we determined this was aqueous. This is a strong electrolyte because it is a soluble ionic compound. Lithium phosphate is a soluble ionic compound, therefore it is a strong electrolyte. Strontium phosphate, however, is an insoluble ionic compound, and therefore it is a weak electrolyte. Lithium chloride is a soluble ionic compound, and therefore it is a strong electrolyte. In going to the complete ionic equation, we're going to have to break up strontium chloride, lithium phosphate, and lithium chloride. Okay. So strontium chloride. Again, folks, this is half of it. You already know the ions. You've already determined the ions. You don't have to go back. You're not going to be going back and figuring out the ions. You've already got that piece. So in our strontium chloride, the ions are Sr2+, and the ion will have the same state of matter as the parent compound, and Cl- with the ion having the same as the parent compound. In other words, look, that top row, I just rewrote it, but now I've included aqueous. This coefficient means I have 3 of these molecules, so I have 3 strontiums. And I have 3 times 2, or in other words, 6 chlorides. My next piece, I'm going to go back to these ions. They're lithium and phosphate ion. The ions will have the same state of matter as their parent compound. Now, I have 2 Li3PO4, which means I have 2 times 3, or 6 lithiums, and I have 2 times 1 phosphate unit, or in other words, 2 phosphates. That's going to go to make strontium phosphate, which I'm bringing down because it's an insoluble ionic compound and a weak electrolyte. The main piece is the fact that it's a weak electrolyte. You simply bring down anything that's a weak or non-electrolyte. And then lithium chloride, I'm going to dissociate into its ions of lithium ion and chloride ion. The ions having the same state of matter as the parent. The fact that there are 6 lithium chlorides means that there are 6 of those units. So there are 6 lithiums and 6 chlorides. And now you have the complete ionic equation. If you can get to the complete, the net is a breeze. If you get the complete right, the net should be a breeze, because all it is removing the spectators. On the reactant side, I have 3 strontium 2 plus aqueous. Do I have 3 strontium 2 plus aqueous on the product side? No. So that comes down. On the reactant side, I have 6 Cl minus aqueous. Do I have 6 Cl minus aqueous on the product side? Yes. So that is a spectator. On the reactant side, I have 6 Li plus aqueous. Do I have 6 Li plus aqueous on the product side? Yes, so that is a spectator. On the reactant side, I have 2 phosphate 3 minus aqueous. Do I have 2 phosphate 3 minus aqueous on the product side? No, so that comes down. And once you get through the reactant side, anything that you haven't discarded on the product side would come down as well. So this literally says that what's going to happen in reaction is the strontium is going to combine with the phosphate to make a solid. Any questions? On Thursday, so I did a double displacement today. Some of your reactions that you'll be performing are single displacement reactions. I will demonstrate how to use Thursday.